Welcome back. Today I want to tell you a real story that never happened. We're passengers on a train, we've got to transmit a file to our headquarters back here. Everything that we send will get printed off in this printer. The problem is, we could run into the tunnel before we sent the whole file. And there's actually some good guys that are after us, but we're not the good guys in this story. So if they stop us from sending our file, we won't be able to print it off at our lair. Meanwhile, at the lair, we've got printer problems. This printer is known to be slow and can jam pretty easily. We hope to print it off successfully, otherwise, what was the point of sending the file? If parts of this story sound familiar to you, then chances are you're from the same generation as I am. And if not, perhaps you need a visit to Blockbuster to check out a VHS. So what's the moral of this story? Sometimes a logical plan is different from a logical outcome. We can see that the plan here is to simply transmit a file from one position to the other and have it printed off. But the logical outcomes could include things like interference from a nemesis, running into a tunnel, transmission noise, getting a simple paper jam. This often reflects the reality of communication, but a lot of other computational tasks. We get our information that comes in multiple stages, and we have to package it for intermediate use. This results in creating a scenario where things could go wrong. And when we try to reason about what things can go right and wrong, we end up straying from our standard deductive logic. Deductive logic, I'll remind you, is the art of reasoning from evidence. Meanwhile, inductive logic is when we recognize that we can't always get all the evidence we need. So instead, we do logical reasoning based on the patterns of the evidence, but we add in a healthy dose of shrewdness. What's likely to happen if we're wrong? In our scenario, we listed a few things that could go wrong. We could have a printer jam, we could run into the tunnel too soon, or our nemesis might interfere. The history of induction is quite complicated. There was an entire era where people were trying to sort out what should count as modern logic, that is, what comes after Aristotle. And the notion of deductive and inductive, deduced and induced, was a good separation of some of the ways we make arguments. We might, for example, think about why does the sun come up tomorrow? It does because, well, it did yesterday and the day before, and no one can remember a time when it didn't come up each day. But that wasn't the strongest argument. It was observed already in the 1900s that there was a need for two types of logic. There was the deductive logic, which we could see as predictable results, where we didn't need extra evidence other than some simplified model. For example, this would capture things like Newtonian mechanics, the work of Galileo, and many other scientists. You could think of many deductive laws, such as, if it rains, then the ground will be wet. If it rains tonight, I can assume before walking outside that the ground will be wet. Even back then, there wasn't a strong line between deductive and inductive reasoning. For example, the reason we believe that when it rains the ground will be wet was probably an inductive reason. We had seen that experience over time and gained some belief in that pattern. But we could accept that perhaps some circumstances would make that change. Maybe it was light rain, maybe the ground was really dry. Whatever the effects might be, we were willing to have some skepticism in there. So the separation between induction and deduction was not very strong back then. Then in the 1880s, mathematicians started to formalize some of what they were doing as well, putting in laws to some of the things they were doing. Dedekind and Peano were two of the ones that looked at the natural numbers. Those are the numbers we count with, 1, 2, 3, 4. And what they observed was there was an inductive process to it. If you already had a number, you could always advance it to the next one. That's something everyone who's ever counted knew. So they wrote down rules. But remember, when we think about data, we think about ways to introduce the data and ways to eliminate it, to use it. Introduction is simply producing the next one from the one you have. So what would it mean to use a natural number? Suppose I want to know my place in a long line. I'm standing too far from the front to tell where the front is. But I know that I'm only one person behind the person standing in front of me. So I could tap on the shoulder of the person in front of me and say, what position in line are you? Now, what the person in front of me could do is they could look around and have the same problem. They don't actually know which person they are in line. They only know that they're one person further than the person in front of them. So they could tap on that person's shoulder and ask them, which position are you in line? And this could go all the way down to the front of the line. And we could then find out which person is number one and hear back from the list of this which number we all are. That's a form of inductive reasoning. It's inductive because the only evidence that I ever possessed was the person in front of me, and I trusted that the pattern was that they could figure out who they were by asking for the pattern to repeat. And maybe the line is so long that it never reaches the front, and we'll never find out. But Our inductive principle was the idea that, well, if what I see in front of me is the pattern, then they should be able to see someone in front of them, and so forth, until finally someone has an answer. This is the nature of inductive reasoning, and it's also very similar to some other words that come in programming, like recursion. Dedekind, along with Giuseppe Peano, both wrote down the rules for counting numbers using this principle, and they called the rule the method of mathematical induction. It was the intention to capture what already philosophers were doing with the deductive and inductive sciences. And because the natural numbers come in a specific order, 0, 1, 2, 3, so forth, it was soon found that that property connected well with ordering things like dominoes, one after the other. And that has become known as mathematical induction. However, we may have overlearned the lessons of mathematical induction, because while it's true that dominoes can teach us some things about induction, there's a lot of examples that occur in our data science world that enhance the way we think of induction today. And that's what we'll be looking at in these next few videos. I'll be using communication as an archetype example of the kind of behavior that occurs when you try to program with inductive principles. Let's take a look at what the big ingredients are. So for today's lesson, let's focus on the general structure of a communication channel and see what pieces of induction we can learn from that. I want to think about the file as some kind of data, but it's data that I'm creating. So let's imagine that we're creating a file. Let's imagine we're typing in the commands that we want to transmit. So what we could see is that we would start with an empty file. Conventionally, that's marked as the symbols EOF, end of file. I can start my file out by entering that token, whatever the end of file symbol is. But that would be a pretty boring file if all I sent was that I'm at the end. So I want the option to be able to prepend some text. So I add to my grammar the ability to add a string. So I can either have a string or a previous file. Each time I update my file by adding more pieces to it. Each time I add a new line to my file, the file gets bigger. Now, I create the file so I know when I want it to end. I simply stop giving it new strings, and that's the one I transmit. Now let's take the perspective of our headquarters. The headquarters has a different problem. It doesn't know when we're going to reach the end of file. And so it simply reads the first piece of text and tries to assume that that's the first line to print. It reads in the line, and it prints it to the printer. What's it do next? It goes back to reading another line. It assumes there's more than one text line. So it continues to read. Now it can read and read and read until it reaches our end of file tag. If it reaches our end of file tag, it tells our printer to shut off. We've successfully transmitted the whole file. But there's a catch. Notice that in this transmission, it's entirely possible that our train enters the tunnel and we lose the transmission. At this point, we'll never receive the end of file tag because we hadn't sent all the file along. What's our printer supposed to do? The answer is it behaves as if it's expecting an infinite stream of data. It's reading and reading and reading and just simply waiting to find out if ever there will be a further transmission. If we put this into a larger reality, we would observe that eventually we would run out of power or we'd get tired of waiting and we'd shut the whole system off. But accepting that the user might get involved, the natural status for our program is to just wait for the next transmission. After all, it could be that we simply haven't transmitted it, but we haven't gone into the tunnel yet. We have to retype that sentence. We shouldn't make any assumptions because we're separated from where it was created. We therefore cannot know what's right or wrong. The situation of this duality is known as data and code data. Data is generally understood to be the finite things you can put into memory. Code data is the kind of things that you read out of memory, and it can be infinite, at least in the conceptual model, as in we don't know if it will ever reach the end. We might have to be in a stance of preparing to read forever, even if we know in reality we'll give up at some point. That's the way that we think inductively and co-inductively. Now there's a little bit more nuance. At some point, I have to provide the information for this antenna to transmit. So I'm actually sending my data through a little transmission unit where it will have to already read the file I'm sending, and it therefore needs to have its own little code data part. I translate the data into code data before transmitting. Likewise, when I receive the code data, I need to send it to the printer, which means I generate new data, the data that a printer needs. The code data of the printer is the printing on the screen. What's the code data of the data? It's the person typing at the machine. So what we can see is what I call the magnet principle. Imagine you had a magnet. Every magnet has a north and a south. Just like any communication is going to have data and code data. But we often look at it at different scales. If we were to crack that magnet in half, we would discover that in separating it, it builds its own north and south all over again. In fact, the law of magnets is that if you were to zoom in and see the little iron filings in between, they're all lined up north to south. The effect is a global effect. Often communications is the same way. We'll have stages that are data-codata pairs all the way along. It's just that sometimes at the scale we care to look about, we connect the data and codata pieces and think of those as plugged in together, and we ignore their subtleties. So we can talk about the data all the way to the codata as the receiver, or we can talk about the channel of how it transmits through the satellite, through the air, and between the printer. These are all the stages of granularity that may or may not matter in your problem set, and many inductive properties are like this. Remember, so there's two things to highlight here. Number one is you have to agree on the scope at which you're looking at. Where is the data being created? Where is it being consumed? Those will have symmetric type relations. The consumer can typically expect an infinite process to take place, whereas the creator will typically have a finite. It knows it's creating it. So if we step back to look at the architecture or our communication example, we start to see some of the mechanics of our general induction and co-induction problems. We see that it's helpful to think about things as occurring as operations, small steps that describe the different possibilities. We could even add into here things like failure. We went into the tunnel, we lost the signal. Loss of signal could be an interpretation of one of the steps. This is similar in spirit to what Dedica and Piano were doing with their operations for natural numbers, only now we're thinking of data sets, and it's wildly more general. We could be building a text file, a JSON blob, a JPEG image, or many other pieces of data. Likewise, we see that there's a dual relationship. For every data, there's a codata model. Sometimes we think of the data first and then create codata to use it. But other times it's the other way around. We might start with codata, receiving a possibly infinite stream, and then turning it into data, the finite parts we bother to read from it. The second lesson we want to take from this is that data and codata often come in pairs. So here's our summary list. All our inductions are going to have a dual notion called co-induction. We'll also have with that a bunch of algebraic operations that model the different steps that could occur. These include constant events like end of file or loss of signal, as well as developed events like add one more line to the file, print one more line to the printer. What we do is we collectively take small basic steps like that, glue them together into larger and larger data types until we have the behavior we want to expect the entire system. Once more, this is planning to be logical, but being smart enough to expect some illogical outcomes, like loss of signal. By behaving inductively, we create a system of logic which is a little bit more like reality. And today, this has also fragmented in a number of other ways. Not only are data types and algebra involved in the study of induction, so too are words like probability and statistics, which take into account how likely some events are. Perhaps you don't have to prepare for the most unlikely event. It is possible that there was an earthquake that shook up the train too, but that's less likely than going into the tunnel. Perhaps you don't need a program for that eventuality. The key idea here is to think about the models that you need to worry about for your application and find the right scientific language to go with it. Induction is a huge body of information, so often you'll need just a piece of the inductive pie. Over the next few videos, we'll be exploring some of these, especially through the lens of data types and some of the diagrams that we can use using the category picture, because these help us build induction and co-induction. A final word of warning, there's a lot of jargon that's used with induction. It can include things like parsing, recursion, co-recursion, formulas,
evaluation,
data and codata, construction, destruction. All these and more get used by many people, but it's not necessarily important that you remember all of them. I found in my experience that no two people completely agree on the definitions of these words, and it can lead to misunderstandings or spirited discussions at the pub.
It's at this point that Algebra Boy recalled an incident with a friend where two of them disagreed on the meaning of induction and recursion. This led to an epic discussion in front of many witnesses. They could not relent on their opinions, and neither one was satisfied by the other one's definitions. However, the fight did not last that long, and in the end, the two were found sharing a meal together again, as friends.
You are, after all, using an English word to try to explain something that's occurring inside of a machine. Chances are that there's more that word could mean than what the machine will bother to do with it. So document your ideas so the next person can follow it. Until next time. That's how you take care of your chalkboard.